Hi everyone, welcome to Big Data Champs, and this is our sixth session, and we are continuing our big data series. And till now, we have covered a lot. And in the last session or last to last session, last I would say last two session, what I have covered is basically how the SDFS architecture looks like and how data is basically stored in the SDFS. So I have explained that in very depth in the session number 5 and 4. If you haven't watched it, please I'll suggest to first watch those session and then come to watch these session number 6. So let's start. And we know how the data is stored on SDFS. So let me recap. What was there? We have a distributed system, and in the distributed system we have a master node and multiple followers node or the slaves nodes. So on the primary node, basically on the master node, we have a primary node, this name node process which is running, and on the slaves node we have the data node process running. The primary name node was basically storing the metadata, and the data node process was storing the actual data like the blocks, because if we store a particular any file in the SDFS, that file will be first divided into multiple blocks or multiple parts, and those blocks will be distributed across these data nodes, or I would say they're stored across these data nodes. Okay, so whenever we create a file, that particular file will be divided into multiple blocks, and each block will be having a size of 128 MB, that is a standard size. And I've also explained why the block size is 128 MB in my earlier sessions, so you can watch that. So we know we have an overall idea how the data is basically stored on the SDFS. Basically, the data is stored, actual data is stored on the data nodes, and the metadata about these actual data is stored on the primary node. Okay, so this is what we have covered. So let's now move ahead with the MapReduce. So let me give an example so that it will be easy for you to understand the concept of MapReduce. So in normal data analysis, uh, you know, you know, consists of two steps. What are the two steps that we basically generally do whenever we do some want to do some data analysis? For example, if we have, let's say, customer data, and we want to calculate for example, we want to calculate the average amount spent by female customer on monthly basis. Okay, this is the analysis that we want to do. We want to calculate average we want to calculate average amount spent by female customers on monthly basis. We want to do this analysis. So in general, the data analysis, basically we divide in two steps. So the first step is we do some pre-processing. In pre-processing, what comes like data validation, data cleaning, etc. Cleaning, validation, some kind of validation. Okay, so this is kind of, or I would say like filtering. So these are some common things that we basically do in pre-processing. And in the second step, we do aggregation. So if I take this example, let's suppose, so what will be the first step? So we will be filtering on gender column, orders placed by female customers. So so we will be doing this processing part, pre-processing part, before calculating the average amount spent. Okay, so if you have different values in a particular column, then you will be filtering on the basis of the condition which is given. Like here we have the female customers, so we'll be filtering on the female gender column. So this is our filtering part which we are doing the filtering, and this is coming under the pre-processing part. We haven't done any aggregation yet. We haven't calculated the average amount. We have just done a filter. So this is come this kind of pre-processing we are doing before going for the aggregation. So in aggregation, what we will be doing is we will be calculating the average amount spent. Okay, we will be using some average function, etc. So this is how the normal data analysis basically we do in 2 steps. So let's now understand the MapReduce. MapReduce. What is MapReduce? What is MapReduce? So MapReduce is it's a framework, or I would say it's a framework which helps us to process the data present on different machines, on multiple machines, or I would say on distributed system. So if we have the distributed system, for example this, we have the distributed system, our data will be present on different machines. So we need some kind of framework, some kind of library, some kind of framework or library which will help us to basically process the data which is present on different machines. Because what was happening in the traditional system, we use like pandas to do some processing and aggregation, for basically to do some analysis. So we use pandas can only process the data which is present on that machine only. It cannot process the data which is present on another machines. So we will need some kind of system, because we have a like whole another system, different distributed system is totally different with the when it compared to to traditional system. Distributed system is like have multiple machines, have master nodes, slave node having the data, storing the data. So we need different framework as well to process the data, because pandas cannot do this processing. Pandas, if you run pandas code on master node, that pandas can only process the data which is present on the primary name node, but we do not have any data on the primary name node. We have the data on the data nodes. So we need some kind of framework which can process the data. If we basically execute a code on primary name node, for example, that program should be able to process the data which is present on data nodes. So there we have the MapReduce can do this. If we execute a MapReduce job, and we submit a MapReduce job to this primary name node, it can basically process the data which is present on the different data nodes. Okay, so that's why it's a library or framework which is written in Java. It is a library written in Java, and we can use this library Java to basically help to basically process the data which is present on the different machine. So MapReduce, in MapReduce basically it follows a particular way to process the data present on different machine. What is that way? It basically process the data in 2 phases. What are those phases? Map and reduce. It processes the data in 2 phases. So map and reduce. So what is map phase and reduce phase? So what will happen in the map phase and reduce phase? Let's see that. So in map phase, basically we will only do the processing part, pre-processing part. So only Pre-processing of data will be done in map phase. What is pre-processing? Let's suppose cleaning, some validations, you know, validations, and let's suppose filtering. There can be multiple, things that we can do as a pre-processing part. Okay, so this is something, the pre-processing that we'll be doing in the map phase. And then the another thing is, in the reduce phase we will be doing the aggregation part. uh, aggregation on uh, results from map phase, whatever be the output of the map phase, output of the whatever the output it will give us. Let's suppose we have done some pre-processing in the map phase, and we get some intermediate output, because this will not be our final output. We will get some intermediate output, because we haven't done any aggregation yet. So this intermediate output, so wait so this intermediate output basically we will be using in the reduce phase, and we will be doing some aggregation on intermediate output from the map phase, and the output from the map phase will be our final output. The output from the reduce phase will be our final output. So what we'll be doing, like if we have a map reduce job, let's say map reduce job, so it will be so we will be writing map logic differently, separately from the reduce logic. So we will be having some map code, and we will be having some reduce code. Okay, in the map code, the logic we will be writing logic for let's say cleaning and filtering, and in reduce code we will be writing the logic for aggregation. We will be writing for aggregation. So your map code will be processed in the map phase, and your reduce code will be executed in the reduce phase. So in your map reduce job, you will be having map reduce code and the location of the file. So basically, like in the map logic only, in the map code only, you might have like specified the location of the file that you want to process, okay, using the map logic and the reduce logic. So you have the location of the file and the map reduce code. So let's see, if you see in the diagram, so we have the SDFS setup in the distributed system. Like you can see the name node process, you can see the data node process, and the data node is basically storing the actual data, the data blocks, block 2, block 3, block 4, block 5, etc. And the name node is holding the metadata, and this metadata is nothing about nothing, just the the locations where these blocks are stored. So basically name node maintains a metadata that we have discussed, and it is basically know which block is stored on which data node. So this mapping is present inside the metadata table, and which is basically maintained by the name node process. So if you submit a MapReduce job, so it will go to the master node, and in the master node we have the name node process. So this name node will check the file location you have specified in your MapReduce code. It will check that location, and it will check, for example, you have specified, let's say, user customer.csv. So you have specified this in your file location, so in your MapReduce code. So it will the name node will check, okay, where this particular file is stored. It will check, okay, this file is basically has 5 blocks, and these blocks are stored on these data nodes. So what the name node will do, name node will basically send, name node will basically send the MapReduce code to the nodes where these blocks are present. So this this name node will send the MapReduce code to only those data nodes which are holding these blocks, which is basically related to this particular file. So your MapReduce code will be sent to these data nodes. Your MapReduce will. So what has happened? Let's go step by step. You have submitted. You have submit MapReduce job to basically name node, which has the metadata. So it know like what is kept where. It know what is kept where, which data block is present on which data node. So your name node will transfer or send the map reduce code, the map reduce code to data nodes where the blocks are stored. Okay, so it will be sent to the data node, to all the data nodes. It will be sent to the all the data nodes, all the data nodes where the blocks of that file is stored. Now what will happen? Once we have the MapReduce code here, your map logic, map part of MapReduce logic will be executed. So your map logic will be executed parallelly on these data nodes wherever the blocks are stored for this file. So the map logic will be executed, and this is the map phase, and this is the map phase, because in the map phase we are executing the map logic only on the blocks. So in the map phase we are utilizing the parallel processing. You can see the data is being processed parallelly on the data nodes. So in the map phase we utilize the parallel processing or the distributed processing, where basically we are able to process the data very efficiently, even if it is a big data. So in the map phase we can utilize parallel processing to efficiently process the data. Once the map phase is completed, the intermediate outputs, the outputs from these data nodes will be shuffled. The outputs from these data node will be shuffled to a data node, another data node. So we will be having the shuffled intermediate outputs from each and every data nodes to this data node. So if we come here, then so this data node will be giving us an intermediate outputs, which will be which will be shuffled to a data node, to a single data node. Okay, so your shuffled output, basically intermediate outputs, will be shuffled to a single data node. So in once you receive the mappers intermediate output, what you will be doing, we will be doing the shuffling, we will be doing the sorting. Shuffling we have done. Shuffling is nothing but transferring the intermediate outputs from the data nodes from these mappers. Mappers are nothing, basically mappers is when, what does mapper mean? Let me tell you. Process when a block is a process when map logic is, or map logic, or can say code, is executed on a data block, on a single data block, on a single. So if you see on the data node, we have the block, only one block, which is block 1. So your map logic will be executed on this block 1 only, because it has only one block. So this is the process we call, like, this is the mapper. When a map code is executed on a single block, data block. So this is what we call a mapper. And if you see on the data node 2, we have two blocks. So a mapper will be running, will run for block 2, and another mapper will run for block 3. So similarly, we will be having, let's suppose, how many mappers we will be having? 1, 2, 3, 4, 5. There will be 5 mappers running. There will be 5 mappers running, and so there will be 5 mappers running. So the total number of mappers is equals to, what we can say, the number of blocks. Number of blocks. So the total number of mappers are nothing but for each block there will be a mapper running. Mapper is nothing but when a block of data is processed using a map logic or map code. Okay, so this is what we call mapper. So once the map phase is completed, all the mappers will basically shuffle their data to the single data node. Once we will receive the mapper data output from the mappers intermediate, because this will be the intermediate output. We haven't done aggregation yet. After aggregation only we will be having our final output. So once we will receive our mappers intermediate output here, we will be doing some sorting, and after the sorting we will be doing aggregation meaning some finding the sum, average, max. This aggregation, this comes under the aggregation part. So the data has to be present, all the data has to be present on a single node, then only we will be able to do the aggregation. And that is like common sense. If a customer customer with customer ID, let's say 123, is present on in block 1, and the customer ID, the same customer with the same ID is present on the block 2 also, and if you want to calculate the sum of amount spent, then these two records, like from block 1 and block 4 has to be present on the same machine, then only you will be able to calculate the sum of the amount spent. You cannot calculate the sum if the records are present on different machines. So if you want to do the aggregation, all the data has to be present on the single machine. That's why we are doing the shuffling. In the shuffling, so after doing the shuffling, so in the shuffling part, what we are doing, we are taking the data from each mapper and putting it inside a single data node. So in this data node, what we will be doing, we will be sorting. First we will be sorting the data whatever we received from these mappers, and then we will be applied some aggregation logic that we have written in your reduce phase. So shuffle. So after the shuffling part, basically the shuffle to a single data node. After the shuffling part, the sorting will be happening. We will be doing the sorting, and after the sorting is done, after the sorting is done, we will be doing aggregation, which is nothing but a reduce logic we have written our MapReduce code. And when we do the aggregation, when we basically execute our reduce logic, when we execute our reduce logic, the reduce logic on intermediates, on intermediate output, it is called a reducer. What is reducer? So when this aggregation will be happening, your reduce logic will be applied on the intermediate output you received from the mapper. That process is called reducer. And this phase, when the reducer will be running, this phase is we call as a reduce phase. So we have done the aggregation, and this is what we call a reducer. This is done on the reducer, aggregation on reducer. And after the aggregation happen, then we will be getting our final output. This is how the whole process runs, and after this final output, this will be sent to the client. So that's how your final output will be sent to the client. Okay, so this is the whole process, whole step, like how MapReduce job basically run step by step. So it basically happen, there will be like two phases. First is a map phase, then reduce phase, and I've explained each phase in you know uh, in the very limited term. Hope you guys have understood. So we have understood the flow, that is okay. And so one more thing is, we discussed like total number of mappers is equals to the total number of blocks. That is fine, because on a particular data node only a single mapper can run at a time. uh, so if we have like say five blocks, then the five mappers will be running. So on the data node 2, even if we have the two blocks, two mappers will be running, but that will be, those mapper will be running sequentially. So first the mapper for block 2 will run. Once that complete, the mapper another mapper for block 3 will run. Okay, so that is fine, total number of block. But if I ask you the maximum number of mappers can run in parallel, it will be equal to the total number of data nodes. The total number of data nodes where our blocks are stored. So we have the four data nodes, and mapper, a particular data node can run a mapper at a time. So the total number of mapper that can run, the maximum number of mappers that can run in parallel is equals to the total number of data nodes. Okay, that's why I mentioned the total number of data nodes. That is fine. So if you have observed, what we are doing is, basically what we are doing in a MapReduce job, we are sending the code. We are sending the code to the machine where the data is stored. We are sending the code to the machine where the data is stored. Okay, what we are doing, we are sending the MapReduce code to the data node 1 where the block 1 is stored, so that our data will be processed on the machine where it is stored. On another way, the data will be processed on the machine where it is stored, it's kept. So we are processing the block 1 on the data node 1 only, and it basically it is stored on the data node 1, and we are processing the block 1 on the this node itself. We are not moving block 1 to any other node. We are processing the block 1 on this particular node only where it is stored. So this is basically what we call a principle of data locality. Principle of data locality. Okay, so this is about the principle of data locality. So till now we have discussed about multiple things, and mostly around the MapReduce and MapReduce job. So we saw a high level picture of MapReduce job, and how, what are the different processes are there, like what are the different phases are there, what is a mapper reducer. We discussed about the same at a very high level. And okay, so now we will try to dive deep into these concepts, and let me start. So basically on data nodes we have the mappers running for each block. So these mapper cannot process the data, let's say in which are in, like, say, CSV, JSON. Instead, what it expect what it expect, mapper basically mapper uh, takes the input data in key value format. It takes the data in the key value format. If you provide some CSV XML thing, then your data or the text format, then basically your that will not be directly processed by the mapper. Instead, like mapper takes the input data in the key value format only. It can only process the data in the key value format. It need the format, key value format. Uh, so how this parsing will be happening, how this conversion will be happening between the because we have provided the CSV format file, and the mapper need the you know data in the key value format. So is there anything that will be helping us? Yes, there is a record reader. So it is a process that runs on data nodes, and what it does is basically mm, parse the data into key value format. So how it does that is basically it split the data which is present in block. It basically split data into records and add the key and add the distinct keys to each record. So it will take your CSV file. If you see, like in the block one is nothing but a CSV file. Okay, so what it will do, it will take the data, a whole data from the CSV file, it will parse it, and basically it will split your CSV file into records. Records are nothing but the each row of your CSV data, and it will create a distinct key for each record. So key will be distinct, key will be generated by the record reader, and the value will be your record from the CSV. So for example, if you have, let's say, your name, age, or gender. So let's suppose we have Rohit, then the age is 34, sorry, then we have, let's say, male. So so what it will do, if you give this data, if you give this data to record reader, this will parse it, and it will create some key, let's say 1 2 3. It will create a key, and it will uh, uh, keep the value as a record, whatever is there. So this is the key value pair it will be creating. This is the key, and this is the value. Okay, so this is how the record reader is basically parsing our data into the key value format. So okay, now let's understand the same thing with an example. So suppose we have some employees data, and we want to calculate the salary for each maximum salary for each department. So in this CSV file, the employee data, we have this information: employee ID, name, department, and salary, and we want to calculate the maximum salary for each department. So we have I'm taking the example. So we have this data node, and in this data node we have this data file, which is like nothing but a block form in the basically stored in the form of block. And so what basically will happen, instead of directly processing this data using the mapper, first we will be converting this CSV format into some key value format using the record reader. So this data, this block will be first processed by the record reader. Basically it will be parsing your data and converting it into the key value format. You can see it has converted into key value format. It has generated the keys, okay, and it keeping the value as a record itself. Whatever is the record, it will keeping that as a value, and it has created the keys. So now this key value format data will be processed by the map logic that we have written in the MapReduce code. So this will be processed by our map code, and this is how what we'll be getting here. So we want to, since we want to calculate the department, the maximum salary of each department, it means we only need the department and salary column. We will not need employee ID and name. So in the map code we written the logic, and we have selected only these two columns. So this will be our pre-processing step that we did in the map code, map logic. This is the pre-processing step. We basically selected the required column. Then this is our intermediate result or intermediate output that will be shuffled to the data node. So your intermediate output, like this intermediate output, will be shuffled to the data node, where what will be happening? First, the sorting will be done. First, the intermediate output will be sorted, and a collection will be created for the values for each key. So if you see, for IT key, it has created a collection for the values of the corresponding keys. Again, like for marketing, similar for the R&D. Why we are doing this is because this will be basically done by MapReduce only. We will not be doing this manually in our MapReduce code. Reduce this sorting part is itself taken care by the MapReduce framework itself. We will not be doing this in our MapReduce logic, okay, or code. Okay, so this sorting part is basically done by the MapReduce. So once we have the sorted thing, because this sorted data help us like to do the aggregation very efficiently. So if we have the sorted data, then the aggregation will be very efficient. It will be very simple. It won't take much time. So this sorted data will be shuffled. This sorted data will be basically processed by the reduce code in the reducer, and we will be having our final output. If you see, from IT we have the okay. Similarly, we have the I think there is a mistake. This IT has to be like this. This should be 1500. Okay, this is a mistake. Okay, that is a typo. So at high level we have understood. Okay, so how the record reader is basically helping us to parse the data, because mapper need the data in the key value format, and record reader process is doing that. This record reader process is running inside the data node only, and this mapper will basically process this key value form data. So this is how this whole process happens. Okay, that is we have understood. Great. So if I want to create this flow, uh, okay, so let me do that. What I will be doing, like if you are the client, you have, let's say, like client has submitted a MapReduce job. So what will happen? This will first go to name node, because name node has the metadata. Basically it know where what data blocks are kept where. Okay. After that, what will happen? It will go to the data nodes, those data nodes where the blocks are present, which has to be processed. In the data node, what we saw is then there is a process called record reader, which is basically parsing the that block which is present into some key value format. So if we have, let's say, block 1, which is, let's say, CSV file. So what it will do, it will read by the record reader, basically parsed by the record reader, and it will basically parse it and convert it into key value format, key value data, which is again processed by mapper, which is again processed by mapper, and we will get some intermediate output. We will get some intermediate output, and this intermediate output, it will be shuffled, and shuffled to the again the reducer, or say one of the data nodes, in that data node. First what will happen, first sorting will be happening, and then your reduce logic will be applied on these intermediate output to do the aggregation, and this is how you will get your final output, which will be further sent back to the client. Okay, so this is the overall flow when you submit a MapReduce job. So let's discuss some new topics, new concepts. What is the time? If you see, what is the time? 4 a.m. almost 4 a.m. in the morning. I'm recording this session, so that is okay. I just need your feedback so that I can improve on the things. Just give me the feedback. Okay, I'll try to improve on those things. Okay, so now let's understand one more thing in this. So we understood, okay, the mappers are something. Mappers are basically depends on the number of mappers, depends on the number of blocks. We cannot define define the number of blocks. So the number of mappers, sorry, we cannot define that. Whatever are the number of blocks are there, those number of mappers will be created. But what about the reducer, where the final aggregation is happening? So in the reduce code, if you see, when the reduce code process our intermediate results, we call that process as a reducer. So can we have multiple reducers? Is there any possibility, and do we actually need multiple reducer? Are there any scenarios? Because we can have multiple mappers, that we understood, that we discussed. We can have multiple mappers, but do we need multiple reducers as well? Are there any situations? Yeah, let me explain that. So can we define the number of reducers? The answer is yes. So the by default the number of reducers is equals to 1. If you don't define anything, there will be one reducer that will be created by itself, even if you are not doing anything in your reduce logic. If you haven't even written your reduce logic, and you have just written your map logic, in that case also your reducer will be running. Maybe it won't be doing anything, but there will be reducer. But you can, if you don't have any aggregation logic, or if you don't want to do any aggregation, you just want to do some filtering, pre-processing, cleaning of the data, then we can set the number of reducers to 0. So what will happen in that case? The mappers output will be our final output. So if we don't have any reducer, then these outputs, whatever is coming from the mappers, these will be our final output. these output, intermediate output, will be our map final output. If there is not any, if there is not any reducer. But can we increase? Yes, we can increase the number of reducer. In which scenario? I'll tell you the scenario. So suppose uh, if we have, let's suppose we have a amount of huge amount of intermediate output. The size of basically the size of intermediate output is huge. And if we just have the single reducer, then this reducer might fail or go out of memory. If the intermediate output is so huge, the size of intermediate output is so huge, then this reducer will might go uh, f- fail. So suppose if we have huge amount of, so if the size of intermediate outputs from mapper is huge, then we may need to increase the number of reducers. Otherwise, the single reducer single reducer will fail as it won't be able to process the huge data. Single So it won't be able to do the heavy lifting if there is a huge amount of intermediate data. Then if we just have the single reducer, then it might fail and it won't be able to do the processing. So in that case, we need in this scenario we need more reducers. So we can increase the number of reducer to process the huge amount of the data coming from mappers. So okay, let me give an example. And basically if we have say more than one reducer, if you see this diagram, if we have more than one reducer, then how the MapReduce process will decide which intermediate result will be sent to this reducer or the another reducer in case of multiple reducer. So how that thing will be handled? So how the intermediate output will be distributed across the reducers. So for that we have a concept of partitions. So there will be partitions created on some logic, and on the basis of that logic, your intermediate outputs will be divided into different partitions. So let's understand the concept of partitions. So since we have discussed we will be increasing the number of reducers, and we will be like needing more number of reducers so that it can process the huge amount of intermediate data that is coming from the mappers. So what we are trying here is basically we are trying to uh, you know implement the parallelism in reduce phase. Because earlier what was happening is in the reducer phase, in the reduce phase, we just have the single data node. So here like we were not doing any parallel processing, like we didn't have any like multiple reducers, and we just utilizing our single node. It is kind of again a monolithic concept that we are going towards when we move from map phase to the reduce phase. Because in the map phase we are utilizing the parallel processing, distributed computing, but as soon as we move towards the reduce phase, and if we just have the single reducer, we are kind of moving from distributed computing to traditional computing, if you at high level if you try to understand. So we are kind of by increasing the number of reducers here, what we are trying to achieve is basically we are trying to induce the parallelism in the reducer phase, in the reduce phase. By bringing the more number of reducers in the reduce phase, we are trying to induce basically we are trying to utilize the parallelism or the distributed computing in the reduce phase, so that if these data intermediate output that is coming from the mappers, these can be distributed across multiple reducers, and we can and this is how like we will be able to process it very efficiently. If we do this processing across multiple reducers instead of doing just on the single reducer, if we do the same processing on multiple reducers, then it will be more efficient because the data will be divided across these two reducers. So that's why we are trying to increase the number of reducers. But the thing is how we will divide the intermediate output uh, into partitions, basically into some parts, so that it can be shuffled across the reducers, across the multiple reducers we have. So how that is done? So basically how the partitioning is done, how the partitions are created, the logic, what is the logic behind that logic. Okay, so it is basically created on the basis of or by using the hash function. So with the help of hash function we will be creating the partitions, basically creating the partitions. And like there are basically like two ways we can implement the partitioning is like either we go with the default hash function, the implicit one, which is nothing but a modulo modulo hash function. I'll explain this in with an example. And another is the custom function. We can write our custom function hash function to basically create the partitions, so that these partition can be further shuffled across the multiple reducer, and we will be able to utilize the parallelism in reduce phase. The next thing is the next question I would you will be having is like how many partitions will be created. How many partitions will be created? We understood. Okay, we will be utilizing hash function to create the partitions, and I'll be explaining how the hash function will be distributing these intermediate outputs across the partitions. But the thing is how many partitions we will need. First we have to understand that. So basically it depends. It depends on the number of reducers. It depends on the number of reducers. For example, if we are using 2 reducers, then we then there will be 2 partitions created. So it means the number of partitions equal to the number of reducers we have. Okay, so the number of partitions equal to the number of reducer we have. So if I go here, for example, this is the output, intermediate output, that is we are getting from this mapper, which is running on the data node 1. So if this is the intermediate output, and since we are here using the only one reducer, suppose instead of this one reducer we have, let's suppose, 2 reducers, one here and this is another reducer, we have 2 reducers. So what will happen, this intermediate output will be divided into 2 partitions, and those partition, like partition number 2 and partition number 1, will be shuffled to different reducers. Partition number 1 will go to reducer 1, partition number 2 will go to the reducer number 2. Okay, so this is how the thing is happen here. For example, let me explain this with an example. So this is, suppose we have the data, I just copied it here. Okay, so this is the data, that intermediate output that we are receiving from the mapper, which is running on data node 1. So suppose we are using, let's suppose, a hash modulo function, sorry. So what is this function? It looks like is like it will take the key and divide it by number of partitions. Okay, so the key is we have in the intermediate output. So the mapper itself is basically giving the output in the key value format. If you see, this is the key and this is the value, and our modulo hash function will be using this key to basically divide this data into 2 partitions. It will be utilizing this key, the department value. So it will be utilizing this IT to basically decide in which partition this record will go. How it will decide? So since we have the key in the string format, so we cannot directly take the modulo with the some integer. We cannot take the modulo of string value. We need some integer value, and how we will convert this into integer is like it will either taken care by internally with by like the language itself. If we like using the Java language, then it will internally taken care by that. Or for now, for example, what we will be assuming is like that internal hash function will basically converting this string value into the length. For example, what I want to say is, though instead of this, it will be converted into, let's suppose, the length of the IT string and 100. Okay, it will be easy to understand. Okay, this is not exactly it will be working, but just to explain you how the data will be distributed across the partition, I'm trying to do that in the simplest possible way. So this is the thing. So suppose the internally this is converted into the length of the string. Since we have the string, we cannot take the modulo of the string. We need some number. So 3 and 200. Then we have 300. Then 3, we have 120. So what will happen now? The key will we have converted into some integer or number. So this is basically internally taken care by the let's suppose programming language, and that programming language is doing it for us using some hash function. Again, that is the different hash function when it compared to the modulo hash function. Modulo is basically deciding on to which partition this record will go, and there will be some internal hash function that will be converting this string into some number. So for example, now if we have this data, let's take this data, and so what will be the partition number it will go to? So it will be like 2 divided by the number of partition, it is 2. We are assuming we are using 2 number of partition. Okay, we are assuming that. We are assuming we have 2 number of partition. Partition is equals to 2. So this will be modulo again. So it will go to the partition number 0. So we are basically counting the partition from 0, like indexing it from the 0. So it will go to, let's suppose 3 divide modulo by 2. It will go to partition number 1. And then we have 3 and modulo 2. It will go to partition number 1 again. Then we have 2 modulo 2. It will go to partition number 0. Again 3 modulo 2. It will go to partition number 1. So this is how the modulo hash function is basically, divided our intermediate output across multiple partition. So we will be having, partition number 0 and partition number 2, basically two partition, and this is how our data is distributed across these partitions. So if I want to show you, so let me show you an example. So this is something I have created. So this is, let's say, the data node, some data node we have, and we have, let's suppose, 2 reducers. We want to use 2 reducers. So in this data node we have this block, and which again has the employee data, and it is parsing using record reader. That these things I have already explained in my in this session only. I have explained these. You can go back to those sections. You can watch these concepts. So this is the data we have in the CSV format, and this is basically passed by the record reader and converted into the key value pair. Then it is basically processed by the mapper using some map logic that we have written, and this is how we got the intermediate output. So this intermediate output is then further divided into 2 partitions that I have just explained, if you see. So using this modulo hash function only, this is divided across 2 partitions. I have explained that. So like you can see, IT is going into partition 0 here. IT is going into partition 0, 2 records, and then R&D marketing is going into the partition 1. Same thing, same stuff. So we have 2 partition 0 and partition 1, which is created again for the intermediate output that is coming from the mapper, this mapper. So this partition 0 and partition 1 basically then further shuffled to the different reducers. So since we have decided we will be using 2 reducers, so partition 0 will go to the reducer 0 only, and partition 1 only go to the reducer 1. So it will not be, it won't be happening like partition 1 will go to reducer 0. It won't be happening. Instead, partition 0 will always go to reducer 0, and partition 1 will always go to reducer 1. This is how this shuffling will be happening, and then further the process will be similar. This partition partition 0 first sorted, and basically then it will be aggregated using the reduce logic we have defined. Okay, and this is how we will be getting our final output. So these things I have already explained, and here also I have explained how the this data is basically partitioned across 2 partition that we have decided earlier. So one more thing just is like we have, like I mentioned multiple times, like the record reader will be parsing the data. So record reader and this shuffling thing will be internally taken care by the MapReduce. We will not be doing this in our code. We will not be mentioning that we will be doing shuffling. We will not be basically writing any shuffling logic or record reader process. So these record reader and shuffling process will be taken care by the MapReduce itself internally. We do not have to do anything. We do not have to worry about it. So this is one more thing that I wanted to mention. So this is the thing, like how the partitioning is working and how the intermediate data is divided across the reducers. So you have understood that. Okay. So let me give you one more example for the same. Like here I have took an example with the data, only a single data node. Let's see how it will look like if we will be having the three data nodes. So let's suppose there is a block one is stored on the data node 1, and similarly 2 and 3 on 2 and 3 data nodes. Our data is basically parsed using record editor, the normal process, and then we are basically running a mapper where our map logic is executed on this block 1, and then whatever will be the intermediate output from this mapper will be divided across two partitions. Since we have decided to use two reducers, then it means we will be having two partitions that I've already explained. If the number of reducers will be equal to the number of partitions, or vice versa. So similarly, like on each data node, the mapper will be dividing its output, intermediate output, into different partitions two different partitions, and then this partition number 0 will always go to reducer 0. You can see on each data node the output from the mapper, and if you see the partition 0 here, partition 0 and partition 0 will always go to reducer 0. The partition 0 from data node 1 also going to the reducer 0, and this partition 0 is also going to the reducer 0, and similarly the partition 1 will always go to the reducer 1. So this is how the like high level picture look like. So we have understood like how the partitioning thing is working, and like how we basically divide the mapper output into multiple partition in case we have the multiple reducers. So I hope you guys understood this concept. Okay, so now let's move ahead, and there is one more concept that I'll want to explain. So this is like one of the picture again I have used. So I want to show you something that you might not have noticed. So what I want to show you, if you see, let's suppose this is a data node 1, yeah, and we have some data, and our goal, what was our goal was is to basically calculate the maximum salary for each department. Okay, this was our problem statement, and we were having like this data set, basically the block which is present on this data node 1, and we are processing it. So record editor was parsing it to convert it into key value format, and then we are utilizing we are basically running our mapper in which we have written our map logic, and we are getting the intermediate output. But the thing is, if you see in the map phase, what all processing we are doing, we are just selecting the columns. If you just see what we have did is like record reader process is like implicit. We do not have to do anything, that I have already mentioned. Like record reader process is like will taken care by the MapReduce. We do not have to do anything with the record reader. We do not have to specify like we have to use the record reader process. It will be taken care by the MapReduce itself. The thing like we did is we written the MapReduce logic. So this map logic is, and in which what we did, we just selected the required columns, the department and the salary, because that is what we required, the maximum salary for each department. And for that we only needed like a department column and the salary column. And we in the map page we just selected these columns only. We did not we haven't done any processing, any heavy lifting processing in the map phase. What all heavy lifting processing or the aggregation we are doing that in the reduce phase, using the reducer. In the reduce code, we have defined our aggregation logic, in which by using which we are doing the aggregation meaning like we are calculating the maximum value, maximum salary for each department. So we are not utilizing this map phase very efficiently, because we in the map phase we are just selecting the required columns. We are not doing any complex processing in the map phase. We are just selecting the required columns, because to calculate the maximum salary for each department. we need two columns, department column and we need the salary column, and we are just selecting the required columns in the map phase. We are not doing any complex computation. Instead, like what we are doing, we are in the reduce phase we are doing this aggregation. We are calculating this maximum salary for each department in the reducer phase, in the reduce phase, using the reduce logic, because in the reduce logic we have defined our aggregation, like the logic to calculate the maximum salary for each department. We have defined that logic, in our reduce code. We have not defined our what we have defined in the map code is we have defined the logic to select the required columns, and that is not efficient because that is very very minimal processing required to select the required columns, but there is like more computation power required to calculate the maximum salary for each department. This is the difference. And map phase, if I show you, like map phase is something that provide parallel processing. Okay, reduce phase uh, does not provide that level of parallel processing, because like we can increase the number of reducer, but if we have the mapper itself, then why we are not utilizing our mappers? Why we are not utilizing our mappers if we have the mappers? We are just selecting the required number of columns, that's it. It is not efficient thing. It is not something that we should do. We should do some complex processing in the map phase because it is providing us parallel processing. Why parallel processing? That I've already explained. Because in map phase we have multiple mappers running. In map phase we have multiple mappers running, and this is something what we call parallel processing. Parallel processing, distributed processing we can do in the map phase. And if we have the distributed processing benefit in the map phase, then we should utilize this. We should try to execute the complex logic in the map phase itself. Why we are just selecting the required number of columns, and why we are not calculating the maximum salary in the map phase? You should have asked this question to yourself, like why we are not doing this calculation in the map phase. Some of the calculation we should do in the map phase. Okay, so case 1, let me do it this way. Case 1, the current case what we are doing, this is the case 1. If I assume this is as a case 1, that what we are doing, map phase, we are selecting the required number of columns, and this require very minimal processing, okay, or compute. This require very, because just we are just selecting the number of columns, okay, and whatever will be the intermediate, whatever will be the output from this intermediate output, this will give us some intermediate output. And what we are doing, we have a reduce phase, and what we are doing, we are calculating the maximum salary using reduce logic in this phase, in the reduce phase. So we have this using this basically intermediate output that we receive from the map phase. Using this intermediate output, we are calculating the maximum salary basically using the reduce logic, reduce code we have defined in the reduce phase. We are doing this using the reduce phase, and this calculation requires more computation, and we are doing this in the reduce phase, and reduce phase does not provide any parallel processing. Map phase provides the parallel processing, and in map phase we are doing very minimal thing. Then what I want to do is I want to shift some of this calculation, I will try to calculate the maximum salary for each department in the map phase. Okay, so how I will do that is basically case 2. case 2, the improved case version, I would say. So in the case 2, what we will be doing, map phase, we will be first selecting the required number of columns, obviously. Then only we will be able to calculate the salary, no? So first we will do this, and then I'm considering this at a mapper level, at a mapper level. So then what we will do, after selecting a required columns, I will calculate the maximum salary. Basically, this is the map code, and calculating the maximum salary is the reduce code. And what I want to do, I want to execute the reduce code and map code in the map phase itself, so that this complex computation will be done in the map phase itself, because we have the benefit of parallel processing in the map phase. So this calculation basically, as I mentioned, this is at a mapper level. Basically, this calculation, this maximum salary will be calculated for each block of that mapper. Calculated maximum salary for each block will be calculated in the map phase, or I would say calculated by the mapper itself. How? Let me show you that. So if you see here, we have this data node 1, data node 2, and let's suppose this is some employees data in the block 1, and similarly in the block 2. And using our record reader, we have parse the data to convert it into the key value format. Then in the reduce phase, what we did, we selected the required columns, and after selecting the required number of columns, then what we did is basically did a local aggregation. Local aggregation means we have executed our map logic, reduced logic here. This is local aggregation is nothing but a reduced logic we have executed in the map phase itself. Basically what we did, we calculated the maximum salary for the data which is present in the block 1. So basically what we are doing is we are aggregating the data which is local to this data node. That's why we are saying it is a local aggregation. This is a local aggregation because we are aggregating the data which is aggregating this data which is local to this data node. Then similarly what we are doing in the data node 2, we are aggregating the block 2 data because block 2 is local to the data node 2. That's why we are saying it is a local aggregation. And then what we are doing, once we have done with our local aggregation, this this output, the local aggregated output, will be shuffled to the reducer in the reduce phase. And here we will be this reduce code will be calculating the maximum salary out of these records that we have just received. And this is what we will be calling a global aggregation. So in map phase, what we are doing is, map phase, we have basically executed our map code plus we have done some local aggregation using the reduce code. And since in the map phase this local aggregation will be running parallelly, because if you see the data node 1, data node 2, these are the data nodes that are running parallelly. So this local aggregation will be very efficient because this distributed data will be processed parallelly. So that's why we shifted this computation or complex calculation to the map phase, because here we are getting the benefit of the parallel processing. These local aggregation is being calculated parallelly on the different data nodes, because earlier what we were doing, we are sending the all the records to this reducer in the reduce phase, and on the single system we are calculating the maximum salary for each department from all the of the data. We were not doing anything in the map phase, and we were just selecting the required columns. So that's how we improved it by using the local aggregation in the map phase. So we executed our map code as well as we did some local aggregation in the map phase, and whatever is the output, the intermediate output, we send it to basically in reduce phase we did the global aggregation on this intermediate output. On this intermediate output we did the global aggregation, and this is the our final output. So this is how we have efficiently did the processing and calculated the maximum salary for each department. So what are the some advantages? And one more thing, before going to the advantages, this process of doing the local aggregation, this process of doing the local aggregation on, or I would say in map phase, we call it a combiner. We also call it as a combiner. That's how that's why I have written it here, combiner. So this process, when we are doing the local aggregation, it is also known as a combiner. So if interviewer asks you, so this is, combiner is nothing but the local aggregation. Okay. So there are some advantages. What are the advantages? Let me explain. So advantages of combiner या फिर combiner or local aggregation. So first is we have shifted our complex computation from reduce phase to map phase. It means we are utilizing the parallel processing by shifting the complex calculation, or I would say aggregation to from reduce phase to map phase. Okay, so this is what the first advantage is there. And the second thing is, since we have done some local aggregation, now the size of the data is reduced. This size of the data is reduced. Earlier we were sending this whole lot of data, the whole block. Now we are sending this local aggregated data. This is like distinct records. Earlier we were having the duplicate records. Now we just have the single distinct records. So the size of the data has reduced, and we are shuffling less amount of data. Because shuffling is also an expensive operation. We are sending the data over some network to the different system, which is through some remote connection. So this is what the another advantage we have. So we have to shuffle the less amount of data. We have to shuffle the less amount of data, less data you can say, or intermediate data. And the third advantage is since in the after doing the local aggregation, so we have done the complex calculation in the map phase also. So basically we have kind of shifted the computation from reduce to map. So now reducer has to do less computation. It means we will require less number of reducer, because now reducer has to do less computation. If we have like more reducers, let's say 5 reducer, and somehow we have shifted the computation from these 5 reducer to the mappers, then instead of 5 we can use the 3 reducers, because we have shifted our reducer computation to the map phase. So the less number of reducers will be required. Hope you understood. Okay, so we have covered a lot in this session, and I've almost completed the MapReduce end to end in this session, and I hope you guys have understood most of the things. And if you have any questions, any doubt, you can please comment in the comment section, and we'll try to revert back to you for sure. So that's it for this session, and we will meet in the next session.